All right. Good morning, folks. Good morning. Morning. Thank you. Appreciate it. One of you, maybe two. No, it's good. Good to have you. Happy Thursday. We are covering, again, some of the basics of control systems today. So here's the schedule for what's going to happen over the next handful of lectures. So on Tuesday of next week, we're going to do a little bit of a pairing session for our controls projects. I'll give you more information about what specifically is going to be going into them. And since we're all here in person, every last one of you, I can count instantly that there are no absences, okay? And that you will get together that's a good opportunity for, if you don't have a group already, you meet people, hey, let's make a group, right? Then after that, we'll make a project proposal. So I will put out a document in the next couple of days that's going to describe what the project proposal consists of. It's going to be a submission to Canvas with a couple of ideas. Yes, what's up?
Just verifying, the project is going to be individual for grad students, right?
That's for the other class. It's okay. I know it's a little confusing. So believe me, it's confusing to me when I'm like, are you in one or two of my classes? I don't know. They're very similar structure. So you grad students are part of a group here. Yes. Great question. Yes, question. It can be a mix. It's a great question. Oh, good. So I can give you this information now before the document comes out. It can be a mix. We're going to say groups of approximately 4 to 5. I do allow exceptions, okay? Especially in the, sorry, I forgot I'm not recording here. Okay, one second here. Yeah. Yeah, what's up? Question in the back.
What are some examples of projects that they did like a previous semester?
Sure, we can go into that right now. Okay, so here are a couple of examples. One thing was, can we create a computer simulation of a Segway, the mall cop scooters? Okay, it's easier than you think, and you do a controller of it, so you just keep it up. Okay, and that's an example of a computer. That's an example of a controls project. Another one is trying to control the speed of a car. You have to make a computer simulation of a car. Okay, and then it doesn't need to be super complicated. Okay, it could be a block with theoretical wheels that drives. You apply a torque, the wheels accelerate, but you want to do cruise control, right? Or lane control, right? Another one is pretty common, doing a simple drone controller, okay? Try to get it to hover in place, again, in a computer simulation. Are we noticing a pattern of computer simulation? It's going to require a computer simulation, which I will teach you how to code. It's part of the class, okay? We'll be using MATLAB for that. And now when it comes to undergrads versus grad students, you can have a mix of undergrads and grad students, but the grad students are going to have to be responsible for a particularly complex component of the project, or complicated component, I should say, not to confuse it with the complex domain. All right? So an example would be that the undergrads might come up with a controller for the linear part of the system. We haven't talked about linear versus nonlinear yet, but linear is easier than nonlinear. Well, a grad student might be in charge of trying to implement a nonlinear component of the simulation and trying to control it, right, on this group of 4 to 5. So just give you a shape of what you're going for. But the core requirement is you're going to need to pick a system that you can simulate. You have something you want to control about it, and you control it. And at the end of the term, you'll have a paper that you'll submit on it and a video talking about, giving a presentation, a preview. So if you want to start talking with your groups now, you totally can. All right? So, and what we will do is we will have a Canvas submission saying, hey, here is our group. That way we have it all submitted, we have it in the system, and that way you know, oh, you're group number 1, you're group number 2. All right? Okay, so that's what's going to happen on Tuesday. Our first quiz, so we're updating the calendar. Our first quiz is going to be a week from Tuesday. So not this Tuesday, but the next Tuesday. All right? You know what's a good place to write this down? On this board here. So let's do that. So today. Yes. Yes.
If your group is all grad students, how do you split that up with the easier side?
Ah, well, you all get to choose complicated sides if you're all grad students, okay? So the best way to think about it is, if you have a group of a lot of grad students, each one of you is responsible for some complicated component, okay? And and I think that one of the better ways to think about it is, let's think of an example. Let's say you're doing Paul Blart Mall Cop scooter, okay? And so you would have to build a computer simulation of the Paul Blart Mall Cop scooter. And let's say you're all grad students. Well, one way to add complexity is to have Coulomb or static friction or kinetic friction involved, because it's a nonlinear way to model friction. Okay, one student's in charge of modeling that and testing out how the controller handles that, trying to make the controller improved. Okay? Another student could say, hey, instead of just trying to keep it upright, we also want to go at a certain speed. That's actually a complexity. That makes it a multiple output system. Okay, we haven't talked about that. Well, we'll talk about it today. All right, you're also curious, so I don't want to leave you unsatiated in your curiosity about your questions. So you have two outputs that you care about, going at the right speed and staying up, not falling on your face, right? Oh, I'm grad student number 2, I'll do that. Okay? So you all, if you're a grad student, you have to have some nonlinear or complicated component that's not easily covered by the course material on linear systems. Okay? All right. Other questions? All right. So, all right. So we're going to do a project group. So we're going to meet up on Tuesday in class. So if you don't have a project group in mind, I recommend being here. All right? Okay. All right. So, but today we're going to talk about components and structure of control systems. Okay? All right. And what does it mean to do this thing called the design and analysis of control systems? Okay? Because here we are controls engineers. That is our job. Okay? As controls engineers, what do? We design controllers and analyze them. Well, what is a controller? Okay? All right. So the idea is that we have components of a control system. Now, a control system has an input, then you have some kind of system, and then you have an output. Okay? All right? And this input here is a thing that we want. Control is about trying to get what we want. All right? And what do we want? All right? And the output is what we got. In our first lecture, we would call this a desired signal. And the output is the actual signal or the measured signal. Okay? And this whole thing in the middle, everything in between, is your control system. Looks so easy when there's just a block on a page. All right? Well, it's a little bit vague, all right? But inside of that system, we have subsystems. We could have a system. I'm going to draw the word system on the outside. Okay? All right. in that system, inside you're going to have processes. Okay? And you have lots of them. I mean, if you think about a car that you turned on cruise control, okay, you could view the input. Your desired signal is you want to set a speed for your car. The output is what speed did you get. But there's a lot of components inside of that system that make that go. One, you have to be able to have a dial that, once you set the desired signal, there's going to be some computer or something that's going to take in that signal and say, all right, thank you very much. I'm going to then send a signal to the throttle, which is going to accelerate or decelerate the car, or not accelerate the car, which is going to, inside of an engine, it's going to shoot in more fuel or not more fuel injection, which is going to combust, and then it's going to cause the engine to actually provide power to the wheels, and the wheels provide power to moving the car forward. So you have a system going into a system, into a system, and going into a system, which ultimately results in the speed of the car. Okay? So lots of sub-processes. So what we will do is we will break down this system typically into a controller, if it's a control system, a controller, so in goes the signal to the controller, and then that controller goes to the plant. Okay? So a plant is the physical system that responds to initial conditions and controller stimuli. It's the physical system. If you're the control engineer, you're probably not changing the plant. Think of it more like a power plant, less like a house plant. Okay? That is the general term within controller. What's your plant within control systems? Okay? So with your cruise control, the plant is the whole car and everything inside of it. Except for the controller, is the system which receives a desired input and sends, I before E except after C, excuse me, receives a desired input and sends an actuation signal to the plant. If it's cruise control, how much do I want to gun the throttle? Okay? But most critically and informally, so the controller is something we get to design. We get to choose as control engineers. As it does not change the design of the physical system. Right? So who gets to choose the controller? You do. Right? It's often written in code these days. Makes it easy to change thanks to the invention of programmable computers. Okay? But again, just because it's written in code does not mean that the most useful way to think about it is code. We will be thinking of these things in terms of equations. We talked about this last lecture. Some of these equations will look like simple relations between, oh, how far away am I from where I want to be? Add a little more oomph, take away a little bit more oomph. That's what P and D controllers are. All right? PD controllers. So they're going to look something like, might look something like this. Right? Where some U of t, that's your control, is equal to some capital K times some V desired, that might be your desired speed, minus V of t, which is your actual speed. Okay? This could be a controller for your cruise control, where this is the speed of your car. Doesn't need to be like this, but this is an example. Now, who got to choose all of this? I did. I just made it up. Hopefully it works. If only you were in a class called Analysis of Control Systems to know. It will work, right? This particular letter right there, K, you'll see it a lot in this class. Just as a preview, it's called a gain. It's a constant. Generally speaking, a positive constant. And as you'll see, if you make those constants negative, a lot of the time, not every time, a lot of the time, your controller will go wild if they go negative. So, all right, that's what the controller is, right? So you can, generally speaking, view the controller is the thing we choose as control engineers, and the plant is the physical thing we don't change. But even within the plant, obviously we're going to have subsystems like we talked about. You have the car, which is going to have the throttle, it's going to have the components of the engine, it's going to have the axles, the wheels, the physical body of the vehicle is all going to be carried forward, right? So inside, we often think of the plant, which has some control input there. It has two blocks on the inside. The first of which is the actuator. And this here is your main process. And the key difference here is that the actuator takes in a signal, something that we want, which might not have a lot of power to it. It just might be a little signal on a wire saying the number 12. Okay, I want 12. And then the actuator's job is to take that signal and do something that has the capability to do physical work on the system, right? If you work in electronics for physical devices, you'll notice there's often a big difference in the power requirements for something that's doing the logic of saying how much you want something versus the power it takes to do that thing, right? If you're an electric car, the power it takes to say I want 50% throttle is not the same as the power it takes to accelerate the car to 60 miles an hour, right? So it's the actuator's job to convert that logic signal into an actuating signal that provides power. So the actuator is a device that provides input that directly drives the system. Example, it does work. Okay? Okay. It does work. And here's some examples. You have the motor on a car. Or if you're doing a pipe flow problem, let's say you want to, here's a control system. I'm going to assume that most of you have showered this morning, and I won't ask if that's the case. But you might have a preferred temperature that you want of that shower. And if you are in a normal human shower that's not super fancy, you got cold and hot, right? Okay? You're like, all right, I like my showers nuclear hot, as my wife says. Okay? So I'm like dialing up the valve a lot, right? And if it's too hot, which is rare, I put in a little bit more cold, right? The actuator is the valve. I've twisted the valve, but then when the valve opens up, that's doing physical work. That's letting pipe flow go through, letting the hot water go through. The valve is the actuator. Okay? Okay. All right. Other examples of actuators. Anyone can think of anything? Yeah.
For the motor, would it be like it would be like the throttle body that gauges how I guess how much air goes into the motor?
Yeah. So like you say the throttle? What you say?
Throttle body.
Throttle body?
Yeah.
Is that what it's called? I'm not a car
It's
guy.
what you're doing when you press the pedal is that there's like a little throttle body that's like a valve where the air goes through, like
Yeah.
from the intake. It basically like opens more as you press the throttle body more to let more air in, and thus create like more power due to the reaction of letting more air react with the gas that's injected into the engine.
Can I say throttle?
Throttle body.
Throttle
Throttle is fine.
Throttle's fine. I was making sure. I'm just sparing my carpal tunnel here. Throttle body. Did not know that. I'm not a car guy. That's good to know. Thank you. Anyone ever cooked before? In an oven? Yeah, I see some shrugs. I don't know if that means microwave or I don't know what that means. Okay? All right? Yeah, I mean, so you have the heating coil. And you put current in and it turns it into heat. Yep. All right? But as mechanical engineers, a good way to think about it is it does some kind of work, or another way to think about it is it changes the physical state of your system. Okay? All right? So those are the actuators. So when you're going to be doing your projects, when you're coming up with your project proposal ideas, I'm going to be asking you, like, okay, what's the actuator of your system? Okay? What's your controlled variable? What do you want? What's the output that you want? Okay? Those are the kinds of questions I'm going to be asking. And if you don't know the answer to that question, then maybe we need to figure it out. Or maybe it's not a controls project. It's like, I want to design a basketball. That's awesome. That might not be a controls project. Okay? All right. So, let's talk a bit about, so what else do we got here? So we also have, so who is cooked? Who has used an oven? Okay, anyone brave enough to tell me something that they have cooked in an oven? Anybody? In the back, you were brave. A frozen pizza, delicious, delicious. Now, tell me some of the steps to cooking said frozen pizza expert.
Taking it out of the cardboard box, and taking it out of the plastic, putting it in the oven, and
Turning the heat on. That's an important one, as well as taking it out of the cardboard box. Okay, turning the heat on. So, do you just hit on?
What?
Do you just hit on the oven?
No, I like turn it to a certain temperature.
Oh, well, you turn it to a certain temperature. Would you say a desired temperature, my friend? You might say yes. Oh, no, I would say desired temperature, but that's probably why I'm not welcome in most people's houses. Okay? All right? So you have a desired temperature. right? So desired, so let's do an oven. What's your name, friend? Mark. Is this your oven?
Yes.
Mark's oven. Okay? He has a desired temperature, as I call it.
425.
Thank you. For frozen pizza?
Yeah.
I've been doing it wrong then. It's good to know. 425 for frozen pizza. Okay. All right. You have a desired temperature, okay? Then something happens where it goes into, so I'm going to make a little longer line here. It goes into some kind of controller. Now, Mark, did you make the oven for the controller for your oven?
No.
I don't either. Even I have my limits. Okay? All right? So we don't know what's going on there. Theoretically, it could be anything. You know, could be an alien inside of your oven choosing the temperature, you know. But that controller is providing some signal to our actuator, which is going to be our heating coil. Which then heats up the actual oven. Okay. Okay. And together, this heating coil and the oven are the plant. And out comes the actual temperature. I'm running out of room. Actual temp. Okay? So, how do you know, Mark, frozen pizza expert, that the pizza's ready to go in the oven?
Well, typically when it beeps, but I just like put it in before it's done.
Okay, so you have so you say typically when it's beeps, but you have your own special pizza recipe where you put it in before.
Yeah.
Okay, well, that's probably a well-kept secret as to why you do that, so I won't probe further. But there's a beep.
Yeah.
The beep. How does it know to beep?
When it reaches the desired temperature.
And how does it know that? How does it know it's reached the desired temperature? Do you know?
Probably a sensor.
Probably a sensor. I would say definitely a sensor. There's a sensor that tells you that it's reached the desired temperature. So the sensor, the way we draw it, is it takes this signal of temperature, and so this sensor will read that and be able to tell us what temperature it is. So a sensor is a device that measures the response of a system. And typically the sensor we'll put as a little signal that breaks off. Okay, we measure. Now when you're cooking your pizza, does the temperature keep going up?
No.
Really?
Yeah.
Doesn't keep going up. How is that? I know you didn't code the controller, so I'm not holding your feet to the fire on that. Well, obviously that sensor is informing the oven to stop heating up more, right? We're at Mark's desired temperature of 425, as we all know is the proper temperature for frozen pizza. Okay? So somehow this controller is aware of the sensing that's going on. It's changing its behavior based upon that measurement. So somehow that sensor is also going into that controller, taking that information and changing what it's doing. Okay? All right. So the way we talk about this is that this sensor closes the loop on this block diagram. Sensors are used frequently to close the loop. on the control system. Okay? Why is that important? So you don't want to burn his pizza. It keeps us from making the temperature go too high, obviously, right? Also, some people are impatient cooks who will go and open the oven and check on something before it's done. It's not enough to look through the window. No, I have to see it up close, right? What happens when I open up the oven? Cools down. Right? How would it know if it cools down? The sensor. And because of the sensor, the controller will change its behavior and you heat it up again, right? All right? That is the benefit of closed loop control. All right, and there are two primary types of control. So, types of control. You have open loop control and closed loop control. So an open loop is going to have a system. In goes some input, then goes into your controller, which goes into your plant. And then there's your out. There's your in, there's your out. This is open loop. Okay? For closed loop, you'll have your in. We will typically have something called a summing junction, this little circle with an X. Its job is to take numbers and sum them, because we're good at naming things. All right? So we will come back to that summing junction soon. All right? Out of the summing junction comes a signal that goes into our control, goes into our plant, and that's our output. But then we take that output, it goes through a sensor, and the way we draw on a summing junction, we will draw that, hey, we want to add that signal. And if we want to subtract the signal, we put a little negative sign. Okay? So the output of this summing junction is going to be this minus that. We're comfortable with that level of math? If not, see me after class. Okay? All right? It's not rocket science, it's just control systems, right? We're just adding. Okay? That is a closed loop. Open loop system, closed loop system. Okay. Now, the benefits of the closed loop system are kind of obvious. You can correct for things that happen that you didn't see coming, such as impatient Dr. Hubicki checking on his frozen pizza. All right? Okay? Now, so benefits of closed loop control. Often known as feedback control. You can correct for unforeseen changes in system variables. That's big. There's a reason that most control we think of is closed loop control. In this room, our room is this temperature because of a closed loop controller. You in the red in the back there, could you look directly behind you, my friend? What do you see?
Thermostat.
You see a thermostat. I also see a thermostat. What does it say out of curiosity?
It says 71.2 degrees Fahrenheit.
71.2 degrees Fahrenheit, right? Someone set it to that temperature, or at least close to it. This is a big building. It can be tough to cool in the Florida heat. Thank goodness it's almost September, okay? That's a closed loop controller. Feedback controller that's making it go. Any questions about that? You might say, well, that's kind of obvious. Why wouldn't we do all control that way? Why would you ever do feed forward control? Can anyone think of why? And that's what this is called. So the benefits of open loop control, that's the opposite. It's often called feed forward control. Can anyone think of why you might want to use feed forward control? Yeah.
Simpler system to design.
Simpler system to design. You don't need a sensor. You don't have, sometimes sensors can be expensive. I have a story about sensing. So, do I have a video of it? Let's see. Give me a second here, friends. Do I have video of this or no? Okay, I'll show this
Which
video
way is
here.
up?
Sure, why not? This is one of our older robots. It's,
So some people wonder
called
why make a
Cassie.
machine that walks around on two legs. That's a
Okay,
great
it's,
question.
oh, look how
a big
young I
reason
look.
is that
That's what I
we walk around on two legs.
first started as a
and
professor,
We
so
design
young and
our
naive.
world around
Okay.
us, so we have to build robots
and
that play.
So this
by our
robot
rules.
is built by a company called Agility Robotics, and it's based out of Oregon. It's a tech company based out of Tangent, Oregon. If you looked on the map, it's literally just two country crossroads. And now I think they have a valuation of a couple $1 billion now because they're working on humanoid robots. It's a spin-off company from my PhD lab, okay, at Oregon State, where is right. That's why I started there. I was a PhD student, and we worked on the predecessor to this robot. It was called Atreus, and when we're doing feedback control or closed loop control on this thing, one thing we got to know is how fast the body is moving or how high the body is off the ground.
So-
we want to make sure that the body doesn't go too low. Okay. Second here. We want to make sure the body doesn't go too low to the ground. We don't want it to go too fast. Well, how do you get a sensor on that? This robot's blind, by the way. No cameras at all. So how does it know how fast it's going? How does it know how high it is off the ground? Well, there are sensors that measure not necessarily where you are in space, but it will tell you how fast you're accelerating. Anyone know what they're called? Accelerometer. They measure how fast you're accelerating. Good name. Okay? Does anyone have an accelerometer on them right now? Where? On your phone. Your phone. All right? And it tells you the acceleration of all kinds of things, including the acceleration due to gravity. So it'll tell you portrait, landscape. Also, it's a big part of how your fitness app works. It knows if you're moving and running, right? Okay, it shows you're running, or there's GPS involved as well. Okay, but these accelerations, it'll measure accelerations. It'll also measure something. There's a gyroscope on your phone as well. You can measure rotation, help measure rotation. But back in the day when we were developing these robots, let me get a better shot of this so you can watch it a little more easily here. Okay. So, what's good? Whole body shot. There we go. All right. In order to get enough measurements to know if we're tilting to the side and quickly and take that information and turn it into how far we've moved, because acceleration, as we know, is the second derivative of position. So if we want to get position from acceleration, we have to do what? Integrate twice, right? So that process is imprecise. And if you have a pretty imprecise accelerometer, which they can be pretty imprecise, then those errors add up. They drift. Okay. Also, we have gyroscopes on these things that are for rotation. Gyroscopes sense rotational velocity. Okay. And so you have to integrate that as well. But you need a pretty precise measurement, we thought, to take that information and get it into a version of a measurement that we actually could use for our feedback control. And back in the predecessor for this robot, we had a very tight deadline, but a very big budget. So we bought the best accelerometer and gyroscope we could find. Turns out, we found out afterwards, these are the things that go on missiles. Okay? Cost $17,000. All right. We really wanted to know where the robot was at. Okay? All right? Expensive sensor. So naturally, if we get away with not using it, that would be great, right? But we felt we needed it. We got it. We got the $17,000 sensor. And so we got this very expensive sensor. We had this very smart undergrad student in the laboratory at Oregon State University. And he said, guess what? It's your job. Get the sensor working. Put it on the robot. So that way we can estimate, what we call build a state estimate as to how fast the robot's moving. And so he said, OK, I'm going to calibrate it. And what do you do with a sensor like this? You would take it, you put it on a table and say, OK, I'm going to calibrate it because it should not be moving right now. It's sitting on a table. It shouldn't be drifting around. It shouldn't be spinning, nothing. And he comes, and next day he comes to me, and the other students are like, I'm just tearing my hair out. It says it's moving. I'm like, I think we have a dud, a $17,000 dud of a sensor. And he worked on this, I feel, for like a couple of days. I'll have to ask Ryan how long it ultimately took him. But then eventually he said, I think I figured it out. The sensor is fine. It says that it's spinning 360 degrees per day. It was so good, it was detecting the rotation of the Earth. And he said, on top of that, it's so precise, I can tell us our latitude on the Earth right now because of this sensor alone, within 1 degree. And so, sensing it can be expensive. Also, sensing can be costly in other ways. We talked a little bit about control systems for things like chemotherapy, for drugs. How do you sense if a tumor has grown? Do a scan, some kind of radiation scan, right? And doctors know you don't do those unless you feel like you should really need to, because you want to limit patient exposure to radiation, right? So the more control you can get out of this without doing a sensing scan for how big the tumor is, the better, right? So, and there are a lot of ways that people have found to make open loop controllers work really well. They've obviously got limitations, right? But if you're really smart about how you design an open loop controller, you can do a lot. Okay? So I just want to say that before you throw open loop control out the window, okay? People use it for all kinds of things. Excuse me. Good. All right. So it's simpler to implement if you don't need a sensor. And by the way, this idea of an accelerometer and a gyroscope together, those two sensors together are frequently packaged in a way that you can buy them into what's called an inertial measurement unit, or an IMU. Okay? Very common if you want something that's moving through space and you want to know where it's going without having to rely upon vision. Okay? All right. So you can think of all kinds of things that examples of sensors, right? You could think of a thermocouple that's in your oven. You could think of, in this case, an IMU, right? A camera is a source of feedback control. Although using that information for feedback control is trickier. It's happening now. It's a very recent advance. People are doing a much better job of using cameras for feedback control. Okay? What's also very common, I'll show you a feedback controller here. This is a drone. This is just set up in the lab right over there. It was for this experiment, okay? All right. And it is dodging out of the way of this pendulum that's coming at it. Obviously, it has to know where the pendulum is.
Here we present our real-time
But
obstacle
if you look,
avoidance
you
algorithm
see
for
that real
varied
quick?
modes of
Look at it.
locomotion.
So this is a paper by my student Jason, who's now working at a humanoid robotics company.
Here we present.
All right, I'm going to pause it right here. You can see those on that pendulum, it's a little foam pendulum, so it doesn't kill our little drone here, right? You see those little silver things on the pendulum? Anyone know what those are? I know Cricket does. Okay, she's not going to say. That's all right, okay. But those are reflective markers, okay? They reflect light. And we have around the lab motion capture cameras that shoot out infrared light, and those reflective markers shoot it back to the cameras, and they aggregate that information to triangulate where the pendulum is, and just feed that information to the drone, okay? That's easier to implement than doing just a camera on board the drone. People are working on those problems, obviously now, they're very actively, but it's trickier to use a camera on board the drone. It's called the egocentric camera because it's on board the thing that's being controlled, okay? So people use cameras all the time, it's just trickier. Question?
How does the drone know whether to go forward or backwards to dodge the pendulum?
Oh, some kind of control system, I might say. So it's using a controller, it's called a model predictive controller to dodge the pendulum, okay? And it's basically choosing the path of least resistance, because what it's trying to do is get back to the center position while not being hit by the drone. And if you're curious, this is the actual paper title. You can look it up. It's on our lab website or even my personal website, okay? But you can see the way that it thinks here.
The feasible space
Put
in
little
half.
fun little animations
This
together.
half-space relaxation
Okay.
lets fast convex solvers
The blue thing is
generate
the
motion
drone, the red
plans
thing is
in
the obstacle.
milliseconds.
It's planning and moving around.
Updating
okay?
the half
We do it
space
for
along
lots
the
of
planning
obstacles.
horizon and
It's a fun
adding a
time.
proximity-based cost enable avoidance of new.
Beauty of feedback control. My student also decided, hey, let's do more pendulums. There you go. There's the drone. Whoop, whoop, whoop. There we go. All right. Okay. I recommend my applied optimal control class if you want to learn more about those types of controllers. Okay. All right. So you can use cameras as well. They're just more tricky. All right. So we've got open loop systems. We've got closed loop systems. Okay? Now let's talk about system response. Okay? We are going to be controlling what we call dynamic systems. Okay? Dynamic systems. Meaning that these are systems whose variables change over time. Seems intuitive, seems obvious, okay, but it's worth stating, okay? Because there's also different kinds of time that we got to talk about in the context of dynamic systems. There's continuous time. That's like, oh, time is a free-flowing, it's a real valued variable, right? It can be 3.25 seconds. It can be 8.96 seconds. 12.29643 seconds. Continuous variables, right? There's also not continuous time, but discrete time, where you're on a clock. Step 1, step 2, step 3, step 4, step 5, step 6. Okay? This is primarily a continuous time system class. We can do some discrete time analysis. That can be useful to even continuous time systems. Okay? Just an example from my own research. If I'm walking, if I want to know if I'm going to walk or fall down, I can do a stability analysis where, yes, I could try to analyze the continuous free-flowing motion of my body, right? Or what's very typical in the field is that when I'm taking one step, boom, 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 boom. Every step, at the instant my foot hits the ground, I take a snapshot of how fast all the parts of my body are moving and where they're at. Then I do it again at the next step, snapshot, right? And analyze those snapshots as two discrete points in time, okay? If you take Dr. Clark's biorobotic locomotion class. He covers this exact technique. It's a very powerful technique. Even though it's a continuous system, you can do discrete time analysis. So we will be controlling dynamic systems. These are systems whose variables change over time. Okay. Okay. And you can say, and that's and as a result, we will model dynamic systems as differential equations, particularly ordinary differential equations. We've all seen differential equations in this class. You're all mechanical engineers, okay? We will do a little bit of solving differential equations in the next couple of lectures, but predominantly we are going to be just setting up the differential equations, doing some analysis on them, all right, to tell us without solving them whether or not our system will work, okay? So a classic example of a dynamic system. Let's not even talk about a robot or even Mark's oven, okay? Let's talk about population. Population. Let's say you got some population, say rabbits. Call it P of T. It's a population. Changes over time. Okay? Or T is time. And we're going to say time is a real number. That little fancy R is a real number. Not complex, real. It's not integer. It can be any kind of decimal number, right? Right? That's the population. I can describe population growth as a ordinary differential equation, ODE, where I say that dP dt, the change in population over time, if it's a population, it's dependent upon the current population, P of T times some coefficient alpha. The more things you have, the more things they're going to make. A kind of exponential growth, right? Well, guess what? If you, can anyone solve this differential equation? Or even just tell me the answer? Yeah. Let's get rid of the alpha for a second. What function, when you take a derivative with respect to time, is itself? Yeah, oh, e to the t, I'll take that. That's right, in this case. Otherwise, I would kill your e to the x with a ddt. Dead. So, all right, okay. Yeah, e to the t. And particularly if you have this alpha, you'd put that alpha in the coefficient of t. So it pops out when you take the derivative, right? So I know by inspection, and from teaching this class many a time, e to the alpha t times some c, some coefficient c, right? That's the solution. If I take the derivative of that, if I take, hey, what's dP dt? Well, it's going to be equal to c. This comes on the outside, alpha, take that derivative, c alpha e to the alpha t. Oh my goodness, isn't that equal to P of t? That this with that, that's equal to P of t. So as a result, that's alpha times c e to the alpha t, right? P of t. Check mark, right? And if alpha is positive, yeah. If alpha is positive, that'll grow. If it's negative, it'll decay. That's exponential growth. Okay? Exponential growth. The more things change, the more things change, is what I like to say. Right? And that's the solution to an ordinary differential equation. What order of differential equation, my friends? First order. First order. Why first order? Because it's got a first order derivative, just one derivative in it, right? The solutions to first order linear differential equations are exponential growth, exponential decay, or exponential nothing. Constant. Okay? Right. So we're going to be formulating these dynamic systems as these ODEs with respect to time. Okay? All right, where was I going with that? So that means we're going to see, let's take a look. Let's plot what happens to our population over time, assuming that alpha is greater than 0. It's going to intersect this axis at time 0. E to the 0 is what? 1. Okay? Sorry, or P of t is right here, right? So e to the 0 is 1. So P of 0 is going to be equal to C times 1, or C. Okay? That is our initial condition, right? And because we know the answer is this exponential, it's going to look like whoop. Oh, no, it's not going to look like that. It's going to look like this. Whoop. Sound effect optional. Exponential growth. Now, in control systems, exponential growth is bad. Something probably bad has happened to your system. Let's say you were controlling an elevator. Is exponential growth a good thing? Well, to each their own. I would say no. Unless you want to create a very thrilling ride. Go apply to Disney for a thrilling elevator ride. Okay? We're in Florida, I can say that, right? People know Tower of Terror and Disney. Okay, I'm making sure. I don't know what the youth are aware of these days. Okay? Right? Exponential growth is bad. Exponential decay is good. Because it means it's probably going to converge to 0. Or you can have decay that converges to a particular point. It might be the place you want to go. Or as Mark would say, desired. Okay? Right? But my point, so that's for exponential growth. Okay? If alpha is less than 0, you get C. This is P of t. This is t. You're going to get exponential decay. Where unlike exponential growth, the more you change, the more things change. With exponential decay, eventually the change kind of stops. It doesn't technically stop. It just, look, it gets so close down at the end, it's barely moving, right? So you can treat it like it's more or less done. It's hit a steady state. Okay? So we talk about the response of control systems in terms of everything while it's changing. Here things are changing. Here where things are kind of steady. I'm just going to try to draw this out a little bit more cleanly. So it's not going back up. I just draw badly. Okay? You all know what exponential decay looks like, right? it doesn't ever get there, but it gets so close. Okay. All right, I'll go back to the main screen. Sorry. Changing. And this is steady, right? We call this region transient, meaning it's still moving. The transient response. And here we have the steady state response. That's after everything is settled out. Let's take the example of an elevator, where we are going to make a normal non-theme park ride elevator. Where you want to go to? What do you desire on an elevator? A floor. Good. We just have a desired floor. Okay. We're going to go put it into a feedback closed loop control system. Goes into a controller, which goes into our plant, which I'm going to draw as plant right here. It's going to have our motor and also our rest of our system. There's two different blocks within a sub-block of the plant. This is the desired floor. Okay. And out comes the actual floor. We measure. You'll notice that I don't put the little sensor box in there, but we'll just assume that there's a sensor box that's giving us a sensor system that gives us the actual floor. We compare these two things. We say, hey, our desired floor minus our actual floor. We have a word for desired minus actual, how far we are away from where we want to be. What is that word? It rhymes with schmerrer. Thank you. It's the error. The error, right? That error will go into a controller, does something, it tries to get the elevator to get up to its proper floor. So let's draw the response of that elevator, the time response of that elevator. You got time. We're going to say the height is, you're reading my mind, z of t, right? We're going to start on the ground floor. This is going to be our desired floor, desired z. Okay? There's going to be some response. If it's a first order response, it's going to look like an exponential decay. Like this. So roughly speaking, this is going to be our transient. And also, and this is going to be our steady state. And you can have a little, it could be a little bit of a difference there. Anyone ever been on an elevator that doesn't quite line up with the floor that you're on? A little gap on the floor? Okay. Well, deal with it, I guess, right? Right? That's an error. This is where you want to be. This is where you're at. There's an error at steady state. And because we're good at naming things, we call that the steady state error. Okay? So that's that difference right there, the steady state error. So the transient response is all about how you get there, and the steady state response is where did you get? Okay? And you can, and if you don't like what you've got, guess what we can change? The controller. Because who gets to choose the controller? We do. Right? There are ways that we can make the transient response, we can make it faster. Within limits, preferably. There's also ways that if this is not a first order system. This is a first order response I've drawn, just exponential decay. I could put, since I decided the controller, I can start putting in math into the controller that adds more derivatives and integrals that will change the order of my system. We all know that first order systems, they'll decay or grow. Anything that a second order system can do that a first order system can't? Can we think of a second order? We don't take in differential equations. What's your classic example of a second order system? Does anyone remember? Mass spring damper. I didn't even have to rhyme to give you the hint. Right? A mass spring damper. They shake. They shake. They oscillate. Guess what? You can have controllers that oscillate. You can make a controller that makes your elevator do this. Not that you'd want that in this case. But you can make your system second order by the choice of controller. Sometimes your system already is a second order if you had a mass spring damper. Lots of mechanical systems are second order. Why? Because of F equals ma, Newton's second law. What's the A? Acceleration. How many derivatives of that of position is that? 2. So you'll end up with a lot of second order systems. Okay? So in this class, you'll see a lot of systems that will behave. They might not oscillate depending upon whether they are properly damped and not. We'll get to that later, right? Okay? But there you have a transient response too. But eventually it'll level out to some steady state error, right? So for response of dynamic systems, we will have a transient response and a steady response, steady state response. If you don't have a steady state response, that's bad news. It means that your system isn't stable. That's a big part of control systems, is the stability of control systems. If there are ways you can make a controller that not only does it oscillate like this, it can grow. That's bad. I've yet to see a controller that I've seen for any system where I said that's good. Unless I wanted the system to be destroyed. Okay? Right? So stability. We will talk a bit about stability in this class. Okay? So there's a lot of definitions of stability. And there's a whole chapter on stability, chapter 6 of the textbook, okay? But colloquially in this class, okay? So in this class, we will say that stable systems have bounded outputs in response to bounded inputs. Bounded input, bounded output. B-I-B-O. BIBO, which I'm sure is an app somewhere. If not, that should be the name of an app. Okay? Meaning that if I give it a bounded input, meaning that if I say this elevator, if I don't give it an infinite amount of torque to the motor, the elevator doesn't go off to infinity, right? If I gave it an infinite torque, good luck. It's going to do something crazy, right? But I give it something that's bounded, some amount of input, right? The elevator does something that's also bounded. It doesn't go off to infinity, right? That's the simplest definition of stability. And the way we will talk about it in practice is that our stable system will decay. toward a final value, okay? A steady state. If it doesn't decay, if it grows, it's unstable. If it doesn't grow or shrink, it's neutrally stable. That's how we'll talk about it in the class. All right? So there's a concept of stability. We will also talk about inputs and outputs. Outputs are the things that you sense and the things that you care about in your control. Let's talk about Paul Blart Mall Cop. Is that right? Does anyone not know who Paul Blart Mall Cop is? It's okay, you don't have to volunteer that information. It's okay. It's a mall cop vehicle, it's a Segway. Okay, you've seen it drive around, right? It's got, let's pretend it doesn't turn for a moment. Okay, that the two wheels on the bottom, okay, you can, that's the actuators you have. They just will go forward or backward. Let's pretend it won't turn, okay? And I can treat this system in a way where I say, hey, I just want to stand up, right? I care about the orientation of me not pitching forward or backward. Don't care at all about speed, just don't fall down, right? What do I desire? I desire that my angle is up, one input. I even have one actuator, which is the wheels. I'm assuming they're tied together here, okay? And then the output is my actual orientation. Do I stay up, right? One input, one output. Single input, single output. All right? We have single input, single output systems. Or CISO. We love our silly names. If it has a single input and a single output, it's a CISO system. This course will predominantly deal with CISO systems. Doesn't mean, all right? Doesn't mean you can't do anything more complicated. There are tricks. And definitely, you can do them for your projects. But the tools we cover in class, first and foremost, are great for CISO systems. Single input, single output. However, if all of a sudden I wanted my Segway to be practical, I wanted to go somewhere, I now care about two things. Staying up and moving at the speed I want to move, right? Two inputs. Okay? I still have one actuator. It's okay. It's not important here. It's not the input, right? And I have two things I care about. Two outputs. My actual angle, my actual speed. Multiple inputs, multiple outputs. What do we think that's called, friends? MIMO. That's right. It's MIMO, right? So multiple input, multiple output. Systems or MIMO. Okay? We will primarily talk about CISO systems for the tools of the class, but we will give you the tools for MIMO systems as well. We're at the end of time today. What we will cover on Tuesday for material is Chapter 2, which are transfer functions. They are a powerful mathematical approach to analyzing and modeling CISO systems. Okay? If you want to, I recommend brushing up on that, looking at Chapter 2. If you need to, look up what a Laplace transform is. Remember those? They're back. Laplace transforms are back, friends. All right. Have a good one.